Yo, yo, yo. What's up, what's up? Welcome back. Today we're working on my x86 operating system that we're developing on stream. It's got some form of base usability, so let's pull up a demo actually. Let's just quickly go to the stream OS folder, initialize this guy. Oops, my little stimulator broke. Why? Let me just pop this guy back open. Sorry, one sec. Whoops. This guy goes here, and he comes in like this. Okay. We have our OS. Let's see if I run it. Do we see something? It's broken right now, because I'm in a bad state. Hold on. Alright. Let me just check my diff. This is not stuff I want. Okay. We're gonna run, release probably. Okay, so we have, a default OS. Sorry, not default. We have like our base operating system, which is just like a kernel that it has like some graphics, some like user input. It has networking. So if I pull up open like a netcat, hold on, netcat to the IP of my operating system, I can like say some stuff on there, and we receive TCP data, and we go back, which means that we have like an Ethernet stack that works, that has like an Ethernet card plugged in via PCI, and we do like address resolution and UDP and TCP on top of that. We're doing this like in parallel, so we have some form of like concurrency, but all on one core. So we're using Rust's async await model to do like multiple things at a time. And we have like memory allocation and logging, so we're like printing stuff to the serial console, which gets forwarded by the virtual machine to standard input output. That's like the current state. And what we're kind of working on right now is we're trying to figure out how to do like multi-core support. So we've kind of been prepping our operating system for a bit to like use thread safe code all over the place, like mutexes and atomics where required. And then last stream we kind of booted up the secondary CPU, so we like ran through this initialization sequence on from that we kind of copy pasted to some extent from the symmetric multiprocessing page on the OSDev wiki. And what happens is like we run like these like very specific. Do these like specific register writes to this specific memory mapped register of this like advanced programmable unorb controller, and we basically say, hey, could you like turn on, and once you're on, could you jump to this like specific address in memory on that CPU? And that's what we got to. There's like this like initialization that you have to do of the secondary processors that we proved in GDB like. That we are jumping to the address that we want, but we didn't prove that what we want to have is happening. So this segment of code, what it's supposed to do is it's supposed to like take your CPU, it boots in like 16-bit mode, it's supposed to like move that into like 32-bit mode, and then set up a stack for us to use, and jump into like this C function where we wrote our version in Rust, and we didn't see that happen. And so the question is, why not? And so that's what we want to look at today, is we want to like see if we can get into Rust, and if we can start running some like maybe useful code, right? Like the goal could be that I want the second CPU to be able to like run an arbitrary function that's been injected from the bootstrap processor. I think that's like a good goal, because with that mechanism, then we can do anything. We can like set up our executors, we can spawn threads, we can do whatever we want, as long as we can just like get a function over there. So that's what we want to work on today. Full disclosure, off stream, I was doing a little bit of probing because I wasn't really confident in my ability to get to where I wanted to get without getting like super stuck. So where we ended last stream was that we kind of got to like this guy. We in GDB saw this, and what I did off stream was I got to the point where I got to like this section where we're in 32-bit mode, and I did like just prove that we have some observable effect externally. And so I'll probably just kind of like replay some of that debugging some of those debugging steps. But it was only like maybe like 15 minutes of work off stream, and then I got to a point where I was like, okay, I'm confident that we can keep going from there. I do prefer to not do that like pre-work stuff because I think that it's interesting to watch the debugging process and the confusion. But just sometimes I have to get a little. I might, if I'm not confident, I might do that. So that's what we're looking at today. So what we got to last stream was one of the things that they do here is they set up this like trampoline code and they copy it into a specific address in like lower portions of memory. And that's because like the API to start up a processor can only ask to jump to a low area of memory to start executing. And so like the question we had was, do we have to do this mem copy? Like, what the fuck is this? Why are they doing that? Couldn't we just ask the linker to put stuff at that address? And we got kind of stuck. Maybe YouTube's the best place to look here. Maybe I look for me. And here, I threw a comment in here saying where we got stuck was right. We put the section trampoline. Okay, hold on. How do I exit this? There we go. So in our linker script, and maybe I'll open up the boot script, the boot file as well. The idea was that there's like, uh-oh, did I lose it? That's not good. How much code did I just delete when I started this stream? Oh, that's gonna be a fucking problem. Oh no. Oh, whew, hold on. I forgot at the beginning of stream, we moved back to a clean state. So let's just check out the right branch. Whew, that was scary. Okay. So the idea was, in our boot script, we have this like trampoline that's this like copy-pasted thing that we want to run to initialize our processor of our secondary processors. And we're instead of trying to do this thing that they do where they have like a symbol and they copy it into this low memory address, I was like, what if we just stuck it there directly in the linker script? And so I defined like my own section called trampoline, and then in my linker script I just said like, go to address 8000 and make this trampoline section. Great. And we got kind of stuck there, but the reason that I was stuck was because I named my section trampoline in the assembly file and was trying to reference it as .trampoline in the linker script, and just obviously that wouldn't work. So if I like make this .trampoline, I'm pretty sure if I build this, give it a sec, and then I obj dump, I think you do obj dump show section, and the section is trampoline. Right, hold on. I did fix this the other day. So section trampoline. Okay. Cargo build release. Obj dump section trampoline. Oh, and that's because I was looking at the wrong kernel. We want the release kernel. Right, so now we are in fact seeing that we have code at the trampoline section, so that's great. And maybe if I, can you do like disassemble? Yeah, we can like disassemble it. And this is gonna look like kind of fucked up because some of this code is in 16-bit mode and the disassembler doesn't know that. But we can at least see the stuff down here in 32-bit mode. That should match up to some extent. So let's look at the boot.s. And we do see that at address like 8060, we have this, like these moves that match up, this CPU ID call, followed by like this L jump at the end. All of that like lines up. Great. So what we should be able to do now is we should be able to just boot and run this code, and theoretically, it should do what we want. So let's look at where we actually initialize these processors, which is in the wrong spot temporarily, but we'll ignore that for now. And I think I called it like boot APIC. Here we go. So in here somewhere, we call this like startup sequence, and this is just like, we'll clean this up later. But basically what we're seeing is we're writing to this register, and this value here says, I want to run the code at address hex 8000. If I change this to like a 4 or 2, it would be hex 2000, hex 4000, hex 8000. Great. And so since our code, according to our obj dump, is like at that address, hex 8000, theoretically, like when it boots, it should just start running that code. And so what happens when I run this? Cargo run, our OS boots. Something happened. Okay. Can we maybe run this in GDB and maybe take a look at what the other CPU is doing? So we'll start we have this like in wrapper script where it like reads environment variables. Like when we say like GDB equals 1, it will like launch the virtual machine in a way that it waits for GDB to connect. So then we can like connect our GDB instance to it. Oops. Oh, it's fine actually. And we can look at the frame2, or not frame2, thread2, and we can see like the CPU is running. Great. But we don't really see it doing what we expect it to do. Right? Like, hold on. How do I do info threads, thread2? Right, like it's just kind of like getting stuck. And so what I ended up doing was, yesterday I looked at this, and there's like maybe 2 things that could be going wrong. One is that there could be like a bug in our code, in our like bootstrapping code. Or 2, maybe the like way that we're putting it there in our linker script isn't working correctly. And so I was like, oh, I'm sure I've seen this before, where in GDB you can just like dump memory. And there's some command, here we go, dump binary address range, here we go. So you can just like dump binary memory to result.bin, and we can just do our address range. So we know that we want our code to be at hex 8000, and we probably just shouldn't have more than like whatever, like what is that, 2 to the, I don't know, hex 1000. We shouldn't have more than that. Shouldn't have more than that much code. So if we like look at this now, we should have this like result.bin, and if I hex dump result.bin, I should hopefully see something that resembles my like obj dump from before. And I just don't, right? Like I want to see like FA, FC, EA, and I'm just seeing like something completely different. And so what that makes me think is that like this linker script thing that we're trying to do is not working correctly. And that might explain why they did this mem copy before. I don't really understand why it's not working. I would think that maybe the bootstrapper grub, maybe it doesn't like us overwriting such low areas of memory if those are supposed to be like reserved for its use. Like I remember seeing, where did I see this? In my linker script, like this, begin putting sections at 1 megabyte, a conventional place for the kernel to be loaded by the bootloader. And it's like, why is that? I don't know. But maybe there's some sort of convention, or maybe like some sort of contract between me and the bootloader that I shouldn't be putting stuff at lower memory addresses until after I've booted. So I would actually just like to see if I put my multi-boot header somewhere else. I wonder if it would do better. If it like maybe it only loads stuff after the multi-boot header. I didn't check this yesterday. Yesterday I just copy pasted the code with memcopy, the way they did it here, where they do this like memcopy to that address. But I did want to see maybe if I put my multi-boot header earlier, maybe it'll get it. So I think I have to make a change in code to force it to recompile. And let's do the same thing here. We gdb run something. No multi-boot header found. Okay, so that's a good indication that like something's wrong here. Unless maybe I have to write keep here, like I did on this other guy. Let's try that. Cargo run. GDB run. It's booting. No multi-boot header found. Yeah, okay, so it doesn't like that. That's fine. That's fine. So what we'll do instead is we'll just go back to our old linker script that just puts stuff in like the text section, like we would like normal. And what we can do is in our boot assembly file, instead of putting this stuff in the trampoline section, we'll just put this stuff down in like the normal text section. And we'll make this AP trampoline a function. Great. And we'll just do the same thing that they did in the sample script. So in our code that boots the second processors, just before we do any of this, we'll just drop a mem copy up here. So I think we have in our crate, we have a libc mem copy, and the destination would be 0x8000 as U8. The source can be, what is the source? It's the AP, what's it called? We have like a name for this function. It's AP trampoline, which is application processor trampoline, as const U8, and the size, we'll just say this. But I guess we could make a global trampoline size. And I can't remember how to, there's like a way to like mark, oh, you just like label. So you say like AP trampoline end. And do I have to like set the size here? Type GNU assembly. Last time I did this, I did just write 1,000. I was like, oh fuck it, we'll just copy a lot. But what are the types? Function, inter function, object, thread local object, common object. I guess it's an object. Maybe I don't have to care. So we'll just say AP trampoline size. I actually don't know how to do this. Maybe I say like section data. And, oh, how do they do this? So they set the size of the function down here. This is where I saw something like this before. So this we already had. But that's okay. We'll just say, well, let's look at what this size thing is. Generated by compilers to include auxiliary debugging information. So that's not what we want. We want to like declare a variable. So GNU is declare variable for C, maybe is the way we want to say it. Here we go. Yeah. So here we'll just say global AP trampoline size. And then we put it in this data section. Align 4, that makes sense. And then we'll say that this is a long of, and we'll say that it's AP trampoline end minus AP trampoline start. Okay, so now we should be able to say here somewhere, extern C, and we have a AP trampoline size, which is a static I32 or U32 maybe. And we also have a function AP trampoline. Okay. So now, instead of typing in hex 1000 here, we should be able to say AP trampoline size. And then here we have to say as U size. All right. So size expression must be absolute. Oh, so here we actually have to do this. Over here, we accidentally left. And okay, that actually surprisingly compiles. I actually am surprised by that. I kind of expected more work there. So let's maybe try to break at the mem copy just to see what's going on. So it's an ACPI, mem copy. So this is ACPI RS line 148. And let's run GDB. We don't need this anymore. Oh, well, we'll need that later. Ooh, it doesn't like that. What doesn't it like? CPU halted. That's interesting. What if I don't do this? Reset. Just to, like, clear my terminal's fucking broken. Let's try running it again. Interesting. So it is the mem copy that fucked me. It'd be nice if we could run in debug mode, actually. So let's just get debugger mode working. I'm pretty sure last stream I saw that debug was fucked. So let's just double check that. Yeah, there's like unaligned pointers that it's trying to access. That's annoying. So we can just clean that up really quick though. If I set a breakpoint in the panic handler, which is main RS line 624. I can break main source, main RS line 624. That'll be hit in the panic handler. I do want to be in debug mode. Oops, in fact, this was debug previously. This should be released. Should have been released before, but whatever, that's fine. And let's cargo run. It's nicer to run a debug anyways for this. We want to run with GDB. So we use our GDB environment variable, and here we do cargo, or GDB-X. There we go. Okay, so we can see where these fuck-ups are coming from. So it looks like the use of copy2 expects align pointers. So this is in ACPI RS line 303. We could just have to replace these with mem copies, which is kind of annoying. So we can say create libc mem copy child u32 as mute u32 as mute u8, because mem copy expects u8s. Oh, I wonder if maybe we can get away with this if we do as mute u8 here. And we can say child pointer as mute u8. Copy to this guy as mute u8, and we copy 4. Maybe that will work. Maybe the alignment stuff is only required for 32-bit pointers. Can I cargo run that and see? So this is ACPI RS line 301. So hit breakpoint 1. Oops, skip that. So this is coming from a different spot now. This is coming from 163, not 331 or 301. So it looks like that did work. So let's just do this again. So let's switch to non-overlapping here because that does seem like smarter. Here we'll say this guy is still going to be as U8, and here we're going to say as mute U8 and 4. So hopefully that fixes this. Can I just kill this guy and then run him again? Oops, so this guy needs to be as mute U32 as mute U8 maybe. Give him a little quick double cast. Nice. This is because this is like a 32-bit thing, so we need to like cast him to a mute U32 and then cast him to a byte pointer, and then like any cast between U8 and anything I think is valid. But casting between like U32 and U64 is like a little bit hairier. For reasons I don't remember. Anyways. So hopefully now my backtrace says that we're at 180. We have problems now. So this is just another one of these guys where we have to convert him to as mute U32 as mute U8, copy 4. Cargo run, source run GDB. We have another panic, and this is at line 183. Oh my god, they just keep coming. So this is as mute U32 as mute U8 for 4 bytes. Okay, one more time. One more time. Okay, continue. Another panic. Oh my gosh, how many times did I make this mistake? Oh my god, it just keeps coming. I guess a lot of times is the answer. Okay, so this is the same thing. Mute GSI as mute U32 as mute U8, 4 bytes, and this guy is going to be the same. So this is going to be as mute U16 as mute U8, 2 bytes. Okay, hopefully this is the last one. Let's go! Okay, very good. Very, very good. Okay. So now we should be back in the state we were in before, where the second thread just isn't doing anything. And why are we stuck here actually? Oh, we're stuck because we're rendering our game too slowly in debug mode. Classic. Okay. So I think we're in a good state now. Let's just add -u git commit -m checkpoint, just so we don't lose that. And where were we next? We were trying to mem copy that stuff over. So we were trying to get our entry point into the right spot. So here, this mem copy should be uncommented now, and hopefully this will work. So I did want to set a breakpoint there. So in our GDB script, I want a breakpoint at line 147. Cargo run. GDB. Okay, so I did want to see what is AP trampoline size. This is like a reasonable number. Hello, no symbol AP trampoline size. I can see it. It's in the line. I guess what we can do is we can step into this function. So we got n is 32. Do you think 32 is right? So this is in the text section now. I guess we can just do this, and we can do the AP trampoline, search for this. So it starts at 50, and it ends at 100. So what is that? P 100 minus 50. 176. This is just wrong. Right? Like, that's just got to be wrong, because we should be at... We should see a size of 176. Unless we're just in the wrong function? What the hell? We are just in the wrong function. Oh, so it's just like kind of like by luck that we happen to be in a memcopy here. That's pretty funny. Because we hit an interrupt in the middle of this. So how do I... I guess what we can do is we can deprint... Okay, here's what we'll do. In our GDB script, we'll write dprintf kernel libc memcopy. We're going to print n is n, and we're going to take in n. So that's a valid thing to write. So here we're going to go into our run script and just drop this guy in here. Oops, like this. And hopefully we should see every memcopy should be logged in GDB now. Hopefully. We're getting ambitious here, but hopefully. Source run GDB. Okay. Okay, cool. So we do see every memcopy. And we are... This is a problem. So maybe we can't do this every time. We can say... Instead, maybe we break on kernel libc memcopy with... I think there's like a condition. You can write like if n equals 176. I think you can do that. So if I cargo run and I source run GDB to restart our thing, that did seem like valid syntax. Okay. And we're continuing. And nothing's happening. But it's probably because we're checking this condition like a million times in the debugger. God, that's annoying. I just want to know if the AP trampoline size is right. Can we maybe look for AP trampoline size in here? So I think maybe in objdump I can just list stuff. Objdump print symbols. What am I looking for? None of these look like what I've seen before. I think maybe I want objdump-x, target, debug kernel, and like grep AP trampoline size. Okay. Am I supposed to be able to see the value in here? I guess we'll grep data with some white space. And maybe this has to be in quotes or something. This is the only thing in data? That's annoying. That's annoying. I want to know if it's right. That's all I want to know. I guess, why am I doing this when I can just print it? This is stupid. So I can just say, AP trampoline size is AP trampoline size. This, we went on a dumb tangent here, but don't worry about it. So, fuck. Info BR, we want to delete this conditional breakpoint because it's expensive. We hit continue, and did we print? All right. So it's fucked. That's the answer there. The trampoline size that we're getting is not correct. So why is that? Why is that? AP trampoline minus AP trampoline. This should be sane. Okay. Well, we'll come back to this. For now, I'm just gonna drop 1,000 in here, like I did yesterday, because I know that works. But I would like to come back to this. So now I think what we can do. What's in my GDB script? I'm breaking at the mem copy and at main panic. Okay, yeah, it seems sane. So we run. I hit next a couple times. What's happening? Why? This next might not work. I might not be able to single step here. Can I break out this line? Let's run again and see if that's mem copy is working. So okay, here we go. So here I should be at that, and now I should be able to do that same thing that we did before, where we dump the memory. I think it's like, what was it? Dump memory binary into result.bin. Address is x8000 to 9000. No symbol results. We have to look it up again. GDB dump memory. Dump binary memory. Of course, not dump memory binary. How stupid of me. Dump binary memory. And so now, if we hex dump this, do we see that our mem copy succeeded, and the like bytes that we get here, do they match what we see in objump? Which should be we disassemble this. We look for AP trampoline, and here we have FAFCEA408000. That matches this. And if we go down like what 40 down to 40, we see BCF CACF. Which actually might not see here. BC. Wait, where did I see that? FCCF. This is at offset. Oh, oops, sorry, that's the start function. My bad. Here, maybe I go down to like, so this is at address 50, so this is at 80, this should be 30 offset, we should see 1F. 1F00108000. Great, that all matches up. And if I go down to like CO minus 50, so what's that? I want to put that in hex. So that's at offset 70. I should see 31CO8E, 31CO8E, D8, 66. Okay, yeah. So now we have proven to some extent that using a mem copy to copy our symbol into the low memory addresses, that's actually putting the code that we want there. Versus what we were doing before, which was trying to get the linker to inject the code there by itself. That wasn't working. We still don't know why. Great. So now we're kind of in this fucked up state though, where let's put this always on top. We're kind of seeing a boot loop now, which is kind of fucking weird. And why would that be? So somewhere someone's like triple faulting. Probably maybe like an illegal instruction. Okay. So I think yesterday I kind of like did some I think I saw this yesterday, and I did some like bisecting. And the trick was just in my boot stuff, I started just like commenting at all of this, right? I just say like, what happens if I run and that whole section's commented out? Great, no boot loop, so we know that it's something related to this. And then I just started like bisecting by uncommenting some sections of code. And like, great, that still works. So it's something to do with like after we execute our startup instruction. Great. And so like what this proves is like when we start up the second processor, i.e. start running code at this address, it's fucking crashing our operating system, and we don't know why. And what do we do to debug that? I tried using GDB a little bit, but GDB is kind of tricky to use on this stuff because when at where we first start loading code, we're in 16-bit mode, which just is like not something that GDB knows how to interpret. But I think, if I remember correctly, we could just try to kill our virtual machine. And we can do that with like a debug, with like a IO port right to this like QEMU device that we're using. So we have this like, what's it called? ISA debug exit. And all this guy does is he says, when you write to this address, 0xF4, I'm just going to crash. I'm going to like exit my virtual machine with an exit code that I flagged the host operating system. And we use this for like unit testing so that like if our unit tests fail, we can flag to the parent system that like cargo test failed so that our linter scripts fail correctly. Great. So I think if I remember correctly, I should just be able to go in here and say like the first thing that we do is an out in like right to that port. So 0xF4. And what's the value we want to write? Like 1, maybe. And if I remember correctly, this is actually how it works. If I go to the IO allocator thing, what we do here when we want to write a U8 is we write ALDX. So this is a register AL, and we write it to DX, where we have to set DX to be the address we want to write to. And we want to set AL, sorry, this goes like this. We want to set AL to the value we want to exit with. And so if I do this, we should see, instead of a crash, instead of like our system boot looping, we should just see it exit. All right, so if I go like this, oops, it doesn't like that because I wrote a percent sign here for some fucking reason. Which we do see, right? We see it exit with exit code 1, and if I try to set like 11 in here, I should see exit code 11 right here. Boom. Okay, so that's really, really good. We've actually proven that 16-bit mode code is running, and it's exactly what we want to run. And so now what we can start doing is we can just start bisecting, right? We can just, instead of doing this here, we can do it down like here. Run it again, and if we exit instead of boot looping, great, that piece of code is running. What if I do it here? Great, that's running. Okay, so where we've gotten to here is, this is the code that's supposed to flip us from 16-bit to 32-bit mode. And what this does is it does a jump to this address, supposedly, right? And if I try to go there, this is where I got to yesterday, where I found that, like, oh, that's not running. So there's something wrong with, like, this jump here. And for some reason, I don't understand exactly what it is. The code that that we pull from this like symmetric multiprocessor page, this is kind of like very carefully crafted assembly code, so that you can say I want to jump to address 8060, and and that will go here. But this in the assembly file isn't actually at 8060. It's at like some random address, and then we copy it to 8000 later. And what I saw in here is if I look at the like dump of memory and I look for where this code is supposed to be at 8060, it's just not there. AP trampoline. Right, so this L8060 is at E0. Hold on, give me one sec. I just gotta open up Python to do some hex math. So here if I go Python 3 and I say like 0x E0 minus wherever this guy started, which is 0x50. And I try to print that as hex. So I say like what? :x dot format or something. This is just 90, not 60. Weird. So if I just write 8090 there, boom, we exit again. So I don't really fully understand why. I assume it's something to do with like this alignment, but who knows? But really, it's the answer here is that we should use like relative labels here, right? So we should say, we could do something like say, section data, section text again here, and we could make a symbol like, well, okay, this is what I've already proven today that I don't really understand how to make like global variables very well. So instead what we'll do is we'll just say we know that this is going to be at loaded to hex 8000, right? So we'll say, well, this is loaded to 8000 at runtime. And so what we should really be doing is we should be doing label offsets here. So we should be doing something like, I think it's, can you do like L8040 minus AP trampoline plus 0x8000? Does that run? Can I like put a $, maybe like this? Or maybe we can say set what is the purpose of this guy here? He's loading the GDT, so we'll set LGDT adder is equal to L8040 minus AP trampoline plus 0x8000, and then kind of put this here, like, oops, this should be a comma here, unequals. Yeah, and that still runs like we want. So we can just start using these. We can just start dropping, we can start replacing addresses with like names. So here, this is 8030, this is the GDT, so we'll just say GDT adder is equal to this minus AP trampoline plus 8000. And then here we can use GDT adder. And here we can run, say, set, what? This is application processor, protected code adder. And this is going to be this minus AP trampoline plus 8000. And here I just write AP protected code adder. Great. Try to run. Let's see if it still does that like exit that we wanted to do. Fantastic. And now we can actually get in here and we could set a breakpoint at this address. So this is, we know at what, 8090 now. So in GDB, we could say break 8090. Run our thing. And can I disassemble? There's like disassemble start to end. So I can say disassemble this stuff, and maybe I have to put a comma here. Here we go. So here that we see that we're at this address, and if I jump to like next instruction, maybe I want like 80 A0 instead of that. See, we're like moving through here, and if I go next instruction, now when I run next instruction, our operating system should quit. Boom, it quit. So we are now like capable of like actually running the debugger in this assembly and proving that like if we hit bugs here, we can actually start debugging them. Fantastic. Yeah, so this is where I got to yesterday off stream. So I haven't got any farther than this, so now we're in like completely unexplored territory. So I think that we've probably proven that the trampoline is running the code that we want. And now we want to say get into Rust code on secondary CPU. So now what we want to do is we want to check this like stack initialization logic and see how this like AP startup code works. So one thing I wanted to try is I just wanted to leave it as is. And in here, we do have somewhere AP startup. Maybe it's in main. We did make a function AP startup that should print HiMic when it finishes. And so I just wanted to see like what happens if we start like do we ever get there? So if I just say like break on AP startup and hit continue. Okay, so we do get here. And does it ever print that? So I don't see it print HiMic, but I do see us crash and restart. And a good reason for that is because it probably tries to return from this function and doesn't know where to go. So I think here if I just loop, and here's the like core arch ASM alt. And I guess this would be unsafe. Because ASM is spooky and scary. Do I see it print HiMic now? So I don't see the print, but I do see the OS is like initialized correctly. And I'm realizing that maybe this is because our IO subsystem isn't initialized yet. So where are we doing, where are we actually doing this CPU initialization stuff? This comes from, how do I use this again? Open. Yeah, here we go. So this is coming from pretty late in kernel initialization. Our IO subsystem should be initialized. And so then the question becomes, well, then why the fuck aren't we printing? So what does our print macro do? He uses this like printer, which is a static variable. So this comes from the IO mod, I think. Printer. This is like a function that has been set with type printer. Printer is an unsafe cell around an option or a box. Okay, so theoretically, this printer function should be valid. So maybe let's, in GDB, try to take a look at that. So maybe we'll, what do? We'll edit our GDB breakpoints and we'll say, I want to break on AP startup, our application processor startup. And what do I want to do? I probably just want to start looking at like that global variable, see if we can see it, maybe step into it. So we'll cargo run with GDB enabled. We'll boot up GDB. We are now here. And if I just start stepping, I don't understand why this just stopped. I guess we restart and try again. Restart, try again. Okay, so maybe we should look at create IO printer. That's not available in the current context. How do I print that global? Create IO printer. Maybe it's known as kernel IO printer instead of create here. Here we go. Okay, so this is a inner, which is an unsafe cell of an option of a box. And can I like print that thing? I guess I can't really tell. Pointer? Yeah, this is an option of a box. Ugh. It's hard to tell. Maybe I can set a breakpoint in. Yeah, let's like take a look at this. So in print, we say if we let this. Can I say like break at print.rs line 7? No. Be source print.rs line 7? No. Yeah, that makes sense because it's in a macro. So maybe what I'll do is instead of using the print line macro, I'll just inline this stuff directly for now. Because I want to get a better idea of what's happening. So we'll say we'll try to get the printer. Otherwise, we'll print. Oh, we can't print something. But we can call IO exit. So what we can do is we can use like exit codes as ways to flag if we've hit certain areas of code because we know printing isn't working. So first we'll try to get the printer. If we don't get it, we'll exit 99. Otherwise, we'll exit 10. And we can just run this outside of GBV and see which one, how we get out of this. And here, I guess, oops, I left some macro shit in here, so I just say, hello, Mick. Interestingly, neither of those branches were taken. What? Why? If I IO exit here, does that trigger? No. Okay. So that's more interesting information. So this IO exit uses another static variable. So maybe our like memory space is kind of fucked up. That seems possible. If for some reason we're not seeing the memory we expect to see on the second CPU. So let's do core arch ASM. And instead of doing this, we'll just write that same assembly code that we wrote before for debugging. Which was what we like moved a number into %AL. We moved a port number into DS? Ooh, I don't remember. DX. And then we did out AL DX. And then we have what? Options, ATT, syntax. So if I run this, hopefully that should see something crash, right? We should see the OS or the operating system close itself. What the fuck is going on? Okay, yeah, here we see exit 10. Okay, so that's a really good sign. So now instead of calling IO exit, we'll just do this assembly block, and we'll do this in the two cases. And here I forgot to copy paste the whole thing. Okay. So here we're seeing exit 99, which indicates that it's taking this branch, which indicates that it's not seeing what we expect to see in create IO printer inner. Very, very strange. Because for sure at this point this shit should be initialized. I think. Let's double check the like startup sequence here. The startup sequence. This isn't happening until. Well, let's just double check. Yeah. All of this is happening under this thing called print headers. Because that's just kind of how the code look. We're in like investigation mode, not like clean code mode. So we have to like remember stupid shit like we're running our code in print headers. So at this point in time, this stuff should be valid, right? If I like IO exit 1, 2 here, that sure does exit with exit code 12, right? And so there's no real excuse for IO exit not to work from the other CPU unless there's some sort of like weird caching going on where maybe because I'm using like an unsafe cell and I don't sync the caches, that's not working. So let's actually try that. If I look at IO mod, maybe what I have to do when I set this guy is maybe I have to like create a memory barrier. Maybe this has to be some, maybe I have to use like atomics here to make sure that like the stuff in the cache of CPU 1 gets flushed to memory. Maybe. Is there like a memory barrier? Rust memory barrier. That just says like, fuck off. Fence. Here we go. Atomic fence. Depending on the specific order, fence prevents the compiler and the CPU from reordering certain types of memory operations around it. Synchronizes with relations between int and atomic operations or fences and other threads. If fence A, which has at least release ordering semantics, synchronizes with its B with at least require semantics, this creates some sort of like happens before. But does this create like cache flushes? It must. But maybe not. Stood atomic rust cache flush. I don't know. Like, all operations on the atomic object itself are atomic. There's a single order for all modifications across all threads. Is therefore about the visibility of other memory relative to some modification of an atomic variable. For example, if one thread sets it out to a value and then sets an atomic value variable, it's agreed upon value. If another thread sees that atomic variable with the value, proper use of the acquire release flags on atomic read-write allows the other thread to also safely access the other data. Okay, so I think theoretically, if there's like some sort of like caching problem, here, maybe I set this to ordering release or acquire, and this to ordering release, and then when I set this IO allocator value on this thread, and then I read it back from this thread, I should see the same data, and maybe that's related in some way. Maybe. So let's go back to wherever my like second process shit is, and try to do like an IO exit 33. We'll say if we IO exit 33, then we're happy. And no, we don't exit 33. Fuck. In fact, we're not exiting anything? That's kind of odd. If I take that out, do we exit? Yes. Ooh, there are some clues. There are some clues there for sure. So let's think about that. Why would that be the case? What if my stacks are getting fucked up because both cores are using the same stack because I didn't initialize them correctly? That seems possible. That seems very possible. I haven't really like validated that code at all. So how can we validate that? Maybe in our when we boot the second core, we can just try to avoid doing any memory accesses after that. So I think I have like somewhere in here boot apic, and here When I send the first startup sequence, I'm pretty sure this is when we actually start seeing code. What happens if I just like infinite loop here? Okay, so we still don't see the thing exit, but that doesn't mean that this like path of investigation is wrong. Let's run this with GDB. And let's say that, let's say that we want a breakpoint here. And this is in run.gdb, we'll just say break here. And then I should be able to say, think. In here, I should be able to boot GDB. Here, I should be able to run GDB. And here, I should be able to see what happens when I call IO exit. So let's step into this and print code. Okay, so the code is 0. That's weird, right? We just called this with 33. We can see that right there. So something's like definitely fucked up. 100%. Hundo P. Can I see like info regs? Can I see like the stack pointer? Here we see our stack pointer as this. That doesn't really help me. Can I like next? Info args. Yeah, the fact that the exit code is 0, that really indicates that our stack is just fucked. And that also kind of indicates that maybe everything is fucked. Can I say like print code equal 33? Okay, so that does set it. That's good. Can I like see? Can't find bounds in current function. Yeah, so something's getting fucked. I think it's very likely that like my stack is broken. So let's take a look at that code. So what does this say? We get the CPU ID, which should be 1 in this case. This like shift right L basically like shakes off the bit so that we get like this should, at this point, EBX should be 1. Here we have EBX is stored into EDI, so it could be passed as an argument to the startup function. Which means that actually we should be able to confirm this. If we say here, let's just exit out here with the CPU ID. So here we'll just say, here, instead of putting this in here, we'll use Rust syntax to say, in reg al is equal to CPU ID. I think this is how you do it. Let's look at the other examples we have in IO allocator. In al, here's how we do it. No reg. And that should work. Do it. So here I should hope to see an exit code 1 here. Let's run without GDB because I don't really want to hit the debugger right now. And I see exit code 0. That's fucked. Definitely fucked. That really makes me think that the stack is just broken. Right, because in boot.s, we get the CPU ID and we're supposed to call this. Let's just... okay, sorry. Then we shift the CPU ID left by 2 to the 13 bits, which is multiplying by 2 to 13. So we have 1 times 2 to the 13 is 8K. Okay. And then we set the stack pointer to our stack, and then we subtract that much from it. So here in our main, we assume that we have 16k of stack. And where do we start? We start at the stack top. So we do go like halfway into our stack, and we assume that that's good. So I wonder if we can like find a way to validate what our stack pointer here is here. Maybe I like set a breakpoint here in GDB, and I wonder if I can just print the stack pointer. I think we already tried that, but let's just see. So we'll run this with GDB. We'll run GDB. We'll get our breakpoint in application startup. So here is our second CPU booting. And here, if I say like info register, our stack pointer is this. So let's just kind of write that down somewhere. And oopsies, what did I just do? I opened to another window. Now if I obj dump this guy, and I look for stack top, how do I like get the data? I want to know like what the value of this guy is. Oh, here. Here we see our stack top is at address 20BFFC, which is like nowhere close here, right? Like absolutely bonkers, nowhere close. So let's just try, right? Let's just, for the sake of testing, let's just delete all of this complication, right? I don't actually, who cares, right? Fuck this shit. Let's instead just set stack top to a number that we think is fair. Which, if we look at this, we could say sub L. Can I just say like I want to subtract 8192 from ESP? Right? That might be sane, right? Then we can at least get rid of some of the complication of this like extra subtraction stuff. We can just do it by hand. And maybe actually what we'll do is instead of stack top and stack bottom here, let's actually say skip 16384 over 2. And we'll say this is stack 1 top. Okay, so now we can say, I want you to use stack 1 top. And we don't even have to do the subtraction. Just for the sake of testing right now. It doesn't like that for some reason. Stack 1 top. Oh, it's because this needs to be like this. Okay. So now we source run.gdb to like connect our GDB instance there, and can I print my info registers? Now my stack pointer is at 0xFFAC. There's no way that's right? Oopsies, this should be nm-c rep stack. Yeah, this is like just obviously wrong. Like, what the fuck? What the actual fuck? So let's look at how we initialize the stack here. Here we just said move stack top into ESP. I did forget. Oh my god. Oh my fucking god. I'm gonna fucking lose my mind. If it's just because I didn't write a fucking $sign in front of the variable name. Oh, I've been bit by this so many goddamn times. Ah! Alright, we'll see. How do I do this? Info registers. Fuck. So I've been hit by this many times. So this is 208,000. This is 209 FAC. Yeah, so we've gone up a little bit. Okay, so the reason for this, I think, is if I type this, move this guy into this guy. I think what that does is it like looks at this value and takes the memory address, like it like takes that as a pointer, dereferences it, and stores like the thing it points to into the stack pointer. And if I put like the $sign here, it says like no, I want like this value actually, like this number. Put this number here. And I think that I just fucked that up. So here, if I go back to doing it the way we were doing it before, I think if I just put a $sign here, our stack pointer should be something sane here. So let's look at that. Oops. So we source run.gdb to restart. And we say what? Info registers. Our stack pointer is something reasonably sane. It is still weird to me that our CPU ID that we get in is 0. That's weird. Let's look to see if let's go back to using IO exit here and see if we get something sane here. So here we'll step into this function and see. So I guess here we'll just say we'll set our breakpoint to when we try to exit, and we'll see if that gets us anything interesting. So we'll cargo run. We'll connect our GDB instance. And code 33. Okay, so we've made progress. For sure, we've made progress. Here we're seeing that before the code here was just like fucked. And now it's what we actually passed in. So that means our stack is working. Let's go! Oh, that's so sick. Okay, so if I continue here, we do see that we got exit code 33, which fucking means that our static variables are loaded from the second CPU. Which might mean that if I fucking print line, so if I just like delete this, we should get into, hopefully we get to this path now. If we're in a good state, we're going to see an exit code 10. Right? Let's cross our goddamn fingers. Not quite. Not quite. We actually saw an exit code 0, which is weird. Let's just try running printline hi make. And let's see if we see that. Let's go! Look at that! Look at that. Okay. That's pretty sick. Pretty fucking sick. Okay, so here we are pretty confident that we're running Rust code on this CPU. That's very, very sick. Okay, so let's think. What do I want to do next? I've kind of left all of this code in like a pretty fucked up state. But I don't think it makes a lot of sense for me to clean that up on stream. I think all of the interesting stuff of like parsing the tables, figuring out how many CPUs there are, figuring out like how to boot the CPU, how to run code on the CPU, where the bugs are, all of that is like, that's the interesting part. And me writing some unit tests and like refactoring some functions to like make them look a little prettier. I don't think I want to go through that exercise on stream. I think it's boring for you, and 2, it's kind of boring for me. So I probably want to just like watch some TV and do that in the background or something tonight. So I think I'm going to call it there, actually. I'm pretty stoked with what we have. We have one CPU, boots a second CPU. Right now we have it in a state where it's kind of like, we still have that infinite loop that we stuck into ACPI here. So let's just make sure that if I get that out, that we still have something signed. Yeah, so we still do see me print HiMech here from the second CPU. And we still do see like our code running. I guess let's run in release mode so that it looks like kind of smooth. Release mode's fucked. Okay. Is that worth debugging now? Yeah, it is. Fuck. Okay, I was gonna say I was gonna call it, but now we're back to an interesting problem. So let's try to figure out where that's coming from. How do we bisect that? So now we're just gonna say fix release mode boot loop. Oops, how did I end up with a timestamp in there? Hello? There we go. And let's make this a little bigger. Okay. So let's put this loop back in here and see if that's related. Yes. Okay, that's interesting. What if I do this? Okay. Okay, so there's something causing a boot loop related to printing from the second core. Does IO exit still work here? Yes. Okay, so it's specifically related to printing from the second core. Okay. Oh, what would be kind of fun is from CPU ID. Yeah, okay. So the question is, why would this cause a triple fault? Let's go back to expanding this. And here we write format args. We write our print line, our hello world in here, or hello Mick, as I like to call it. Take a quick little peek there. And so we're back to boot looping, great. And here, we'll put in our little IO exit. So we should see that we get our pointer and we exit 33. Okay, so it's something to do with like the right implementation. So probably what we can do is we can set a breakpoint here. So I can go into my GDB script. I say breakpoint here. And when I breakpoint there, I want to set another breakpoint at line, where do I want to set this breakpoint? I probably want to set it in like the serial console printer or in my printer over here. So somewhere we should eventually get into this like print function that we set up in main, that we register with our print handler. So it's somewhere in here. I think it's in this inner. Yeah, here. So here I just want to put a breakpoint here and see if we ever get to this point. This is going to be release mode kernel now, because we're in release mode. We have release mode problems. And yeah, let's try running GDB here. So here we source run.gdb. Where are we? We're at AP startup line 99. What the fuck? Is that where I expect to be? I don't remember setting a breakpoint there. Oh, I did. I just have to hit continue. I forgot to hit continue here. But then I have I've got write string for my kernel interrupt handler. Interrupt guarded inner write string. Where am I? Oh no, I'm in the right spot. So here I'm trying to write FD0000. Where is this coming from? What the fuck? This is coming from kernel main get frame buffer info. Okay, we'll just continue. We don't need this one. That's not what I'm worried about. I'm worried about the write from the CPU 1 or CPU 2. right. Which I'm still just in the wrong spot. Here, what we'll do is we'll go back to my ACPS stuff. We'll disable all code running on the second CPU, the first CPU again, just to simplify the debugging thing. So here, after I boot, I just loop forever. And that should make this debugging simpler. And I think here in run GDB, I wanted to hit continue here. There we go. Okay, so I source my GDB run script. And here we go. So, what the fuck? I shouldn't be seeing this backtrace. What the fuck? Why is my infinite loop not happening? I'm confused. Cargo run release. Oh, of course I'm not seeing my infinite loop because in main, in my AP startup here, I need to move this loop up. Gosh, okay. Here I should see an infinite loop of me printing high. But I don't? Hello? What the fuck is going on? Oh, oops, because I have my infinite loops up here. My bad. Let's try this again. Cargo run release. Okay, so here we do get stuck in this infinite loop, which means that the only time I should be printing high or printing anything is from the context of AP startup. And here I crash. Great. So let's go back into my GDB script. Holy shit. I'm running my release kernel. I'm breaking at main rs99, which is here, right here, at main 90s99. I'm then saying I want a breakpoint at main rs133, which is where I write this. And that's the only place I should be seeing that from. Okay. So GDB equals run. Cargo run release. Source run.gdb to restart my GDB context. And here I am in main rs135 in my write string function. Let's just double check that that's the right thing. 135. I am in fact in write string, like I wanted. And this is just coming from a fucked up spot. Like, why am I on thread 1? Why is CPU 1 halted? I should be on CPU 2 right now? Right, thread 2 hit breakpoint 10, and then thread 1 hit breakpoint 11. Thread 1 shouldn't do anything after thread 2 started. Thread 1 should be stuck in my infinite loop. Why is it doing anything but looping forever? Holy shit. Interrupt causing thread 1 to print or something? It shouldn't be though, because we're in multiboot to get frame buffer info. Which, is this like out of order execution? Where the fuck is that coming from? This is main 2059. This is just coming before the other stuff. What the fuck? Can I just hit continue? Where? So it does kind of feel like there's like some sort of out of order execution happening, which might be related. Can I... Fuck. That's annoying. Okay, well, we'll just keep hitting continue and backtracing. And just wait until I see it from thread 2. Where is this coming from? This is coming from, like, I'm now getting, like, the RDSP stuff that I was trying to print before. Oh yeah, this does make sense. Maybe there's some sort of like deferred execution. No, 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 no. No, 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 no. This. Oh yeah, I guess this stuff should be. Like the CPU was initialized here. Why is this stuff still happening? Maybe my infinite loop is getting compiled out. That's possible. If like, if for some reason, Rust decided that this isn't happening the way I expect it to. Oh, wait, no, hold on. Oh, I'm an idiot. This just triple faulted. Oh, I see, I see. We got here, and then we immediately jumped back in time because we set the breakpoint and it never got there. Ah, ha ha ha. There we go. Okay, so yeah, we set the breakpoint. OS restarts. We then hit that breakpoint in an earlier spot in our program run because we just restarted the OS. That makes sense. That makes sense. Okay, so then the question is, that means that we're just never getting to that point in code. It means that we're crashing in core format right before we actually write it out. So if I go in here and I go into main, I go to AP startup. I might be able to call directly printer write stir hello. And if this is working, then maybe we don't see our crash. Cargo run release. Okay, that looks different. I still don't see it get printed, but I'm not seeing the triple fault I was seeing before, so that's a good sign. I guess theoretically I could be like clobbering stack. So let's go back here to just writing stack one top directly and not trying to do this like shift math. I'm still not seeing this. What happens if I cargo run release over here with the way it was before? Triple fault? Yeah, okay. I'm missing something. I'm missing something for sure. What could it be? Let's think. I guess let's try debug mode. Let's just make sure if I write like printer write stir hello mic in debug mode, this should do what we expect. And it does. Okay, so that means that we are calling the right API. It just means that in release mode, this write stir is doing something that we don't expect. Let's try to think about it. Think about it, think about it, think about it. What the fuck is going on in that write stir? So this guy is an implementation that's defined in interrupt guarded init. Where that is this function here. Self-serial write string. Let's take a look at that. He does nothing crazy. He does self-write byte. So he says, while the transmission is not ready, write you. I guess we could just breakpoint here. Now that we know that we're in the right spot, and we'll see if we can see where it's crashing at this point. So we run gdb, cargo run release. We reload our gdb script to restart execution. And that's interesting. Why is nothing? We've just frozen now. That's new. So because we just didn't hit that point in code? What the fuck? Okay, what about this point in code? Do we hit this ever? What the fuck? Okay. So where, whoa. Self 0x0. Okay, here's a good fucking clue. Okay. So thread 2 did get to write string. He's got self as 0x0. That's fucked. That's obviously wrong. So how could that have happened? So here he registered himself as a serial writer. Also, if I look at my backtrace, that's fucked too. I see 0, 0, 0, 0, 0 in my backtrace. So how does the backtracing work again? I think I have my frame pointer and my stack pointer. And I think x86 frame pointer. If I remember correctly, there's just a register that says where I'm supposed to return to. EBP, that sounds right. So info registers. So here my EBP is 0x0, which is fucked up. And I think probably if we look at our other thread, and I look at where I am, I'm like in some printer function. And if I look at my registers here, EBP is 136778. If I backtrace, I thought that I should see 136678 somewhere in there, but maybe not. Oh, EBP, that's the frame pointer, is maybe the beginning of the stack. My bad. Where does the return address get stored? x86 return address location. Usually on x86, when using std call convention, return address stored is at the content of EBP plus 4. There we go. So here, if I print what? The memory at EBP plus 4. How do I do I put $sign EBP? EBP plus 4. Yeah, here we go. And then I say star, to dereference EBP plus 4 as mute U32. And I print this as hex. Here I should see this. Okay, cool. Cool. So what we have, we'll draw it out. So we have memory. This is our stack. So when we jump into a function, we'll say that our stack pointer is here. This is our starting point. We set frame pointer to where the stack pointer was. And then we put stuff in here. So we'll say 1, 2, 3. Then we set the stack pointer here. This is where we call the function. What they're saying here is actually before we put 1, 2, 3, we put the return address. Or maybe the return address comes. This might be wrong. Hold on. I think it's very slightly different. I think it's I put arguments onto the stack, then I set the frame pointer to here. Then I set the return address, so wherever I was called from. We'll just put that ret. And then local variables go in here as we move the stack pointer up. And then what happens is after we pop our stack pointer back here, stack pointer should equal to frame pointer, and then we'll have the return address. So that's what we're saying here is we should be able to see the return address at the frame pointer plus 4. Oh, that's maybe I've got the arrow. Maybe this goes here instead of here. I don't know, something like that. Anyways, frame pointer, fixed spot when we enter function, doesn't move till function ends, has the previous return address near it. What we're seeing on thread 2, i.e. CPU 1, we're seeing a backtrace of that's fucked, and that's because if I look at my registers, my frame pointer, EBP, also fucked, and our stack pointer, this guy looks maybe kind of sane. Can I like maybe inspect that guy? Let's think about this. Maybe I didn't set the frame pointer on my initial thing. Maybe I should also set the frame pointer like this. And maybe there's something fucked up going on there. Although it seems like in our once we're in AP startup, any further function calls should do that. So let's look at AP startup before we go into this right stir and kind of look at our registers there. So we can go here, we can set our breakpoint. Right. And let's inspect the registers at that point, then after the function call, and kind of see if there's like, if we can see where the like fuck ups are happening. So I don't think we need this one anymore. I'm gonna close this because there's too much shit going on. We'll cargo run. And then we will source, oopsies, we'll run GDB. Okay. So why didn't we hit? Oh fuck! Sorry. I fucked up my script. This has to go. We'll go like this. Cargo run. I just fucked up my breakpoints a little bit. I put them in the wrong spot. Okay, so here we are just before we call this function. And let's see. We have a stack pointer who looks sane. Frame pointer who looks completely insane. I wonder what happens if we, at this point, set our frame pointer to our stack pointer, just to see. So let's say set EBP equals ESP. Okay. Now let's continue. Oh, okay. Oh no, that's not good. So here we had our stack was at 1 through 2 FF8. Where are we now? Oh, here we go. Info registers. Now we're in the right function. We still have our stack has moved down a little bit to FCC FF8. We still have our back traces fucked up. Let's think. I'm gonna restart. I want to go back to the other state, like our just before we call. I just want to see what it looks like. Let's see. How do I do this again? Source run.gdb. Okay. So let's look at my breakpoints. Cool. Let's look at my registers. And look at my arguments, maybe. So I will just note that the fact that my CPU ID here is 0 is like fucked up. I'm pretty sure that's wrong. How do I look at it? P kernel CPI CPU ID. Hold on, let's double check that. I'm pretty sure that this should be 1. Like almost fucking positive. So let's just see. Here I have a CPU ID function. Let's make it public. And I think that I should just be able to call that from within GDB. I think. Let's run debug mode. And if I'm running debug mode, I have to fix my GDB script to load debug for debug kernel at the release one. And let's source run.gdb. So I think I can say print kernel ACPI CPU ID. Oh, it doesn't like that. Oh, it just crashed. Fuck. Fuck. Hold on. There's a way to prove this. Let me think. If I go back to my AP startup, instead of trying to print something which I know crashes, I can just try IO exit CPU ID, which comes from kernel ACPI. So here I'm hoping to see that I exit 1 here, not exit 0. And I did exit 1. So the fact that the CPU ID that I'm getting passed in is not the CPU ID that I'm exiting with is kind of surprising to me. Let's just also confirm really quick that if I do this like early in main, that I do see an exit 0. So I think I should just be like, drop this guy here. Just to, oh no, not here because he won't be initialized. Just somewhere before we do our other initialization. Yeah, so there I see an exit 0. So that proves that this like CPU ID stuff that we're getting, this implementation of CPU ID is in fact giving us a different number for different CPUs. Great. But we should be seeing the CPU ID passed in on AP startup. This should fucking match. And why does it not? Why? So let's go back and look at our boot script. And here, what are we fucking doing? We're moving 16 into AX. Why? Moving AX into DS and SS. Oh, right, okay. So this is setting up our like global descriptor table stuff. Sure. Here we move 1 into EAX, just like we do here. We call CPU ID because that like triggers this special CPU ID mode. I don't know, it's a complicated command. Just trust me that says like we should be putting in the number 1 to get a CPU, get our ID, and then we should be shifting EBX by 24 after. So here we shift EBX by 24. We move EBX into EDI as like a temporary variable. Then we like do some shit to set up our stack. We actually don't need to do this. We actually don't need this EDI stuff because we're setting our stack directly. And then we are jumping to AP startup. So here at AP startup, the stop of our stack should have a 1 in it. So if I cargo run, release, if I'm not seeing us exit with exit code 1 here, that's like a big problem. I'm not seeing us exit at all. That's odd. That is very odd. Why would that be? Is it because I'm not doing something here that I expect to be doing? Let's just make sure that if I type anything in there, it does exit. Yeah, okay, that's doing it. Let's try doing it debug mode. Maybe there's like something about release mode. We already know release mode's broken, so let's just punch in CPU ID here. Oops, ACPI, CPU ID. So we see exit code 1, great. And if I put in CPU ID that's passed in to us, as U8, he's getting a 0, right? So something here's just fucked up. So maybe what makes sense to do is try to debug that. Maybe that's a good clue as to why everything else isn't working. So here, I'm going to set my breakpoint here. Oops. And what we're going to do is we're just going to try to look at the stack and see if we see CPU ID 1 in there. Oops, this should be GDB equals 1. And then here we should run with GDB. And so here we have CPU ID equals 0. Okay, fine. But what if I look at the info registers? Okay, so here my stack pointer is at 209 FCC. So what we should do is we should check where do we expect this to be? And so I think it's objdump or nm-c is what we're doing. We have stack 1 top is at A0000. So us being at 9 FCCC kind of makes sense. That's how many bytes below? So we have this guy minus this guy. So we're 34 bytes further down on our stack than we initialized it at. So can we maybe print the memory at those addresses? Can I just like print memory? I guess I can say print hex as U32s or something. This guy. Oops, I can't cast that way. I have to do as mute U32. Getting my like C and Rust syntax mixed up. And then can I print like 32 over, or 34 is gonna be 4 times 9. Okay, so what's interesting here is nowhere in here, nowhere, are we seeing the number 1, which we should, because when we called CPU ID from our trampoline code and pushed that onto the stack, we should see that. Yeah, there's something fucked here. So maybe let's just do this. Can I just make this a naked function? Don't fuck with my, don't do anything, please. Just, oh, actually what makes more sense is we should check, we can just set a breakpoint at this point here, before we call this. So where does that come from? If I obj dump, disassemble, look at AP startup, not AP startup, we want AP trampoline, sorry. The trampoline, we should find the place where we're gonna jump to our AP startup, which is here, I think. And so we can just set a breakpoint at F7 minus whatever it is, F7 minus the start, which is 50. So we can say 0x F7 minus 0x 50 plus 0x 8000, which is where our code goes, and we want to put this as hex. We'll set a breakpoint here. Okay, and at this point, we can like look at the registers and see why the fuck we're not seeing what we want to see. So GDB equals 1. We source run.gdb. We have a breakpoint at this specific point. We hit the breakpoint. We look at the registers. Here in EBX, we have 1. Okay, so that's a really, really, really good sign, right? This is what we expect our CPU ID to be. We expect to be 1, and we expect to push this on the stack. So then the question becomes, why the fuck does this not go on the stack? Here, our stack is here. Now our stack has moved because we pushed to it. And can we like can we print the value there? So let's print as hex this address as a mute U32. Oh, I guess we're in C lane now. Fuck. This is assembly, so oh no. Oh, my brain. In star. So why the fuck are both of these still 0? We just pushed a value to it. Right? Right? Like, am I crazy? Like, if I disassemble this guy, I think it's like this. Here, I just pushed this value on the stack. I literally just did it. So, like, what the fuck, man? Right? Like, info registers. I just pushed EBX. EBX was 1. So why am I not seeing that anywhere on my stack? At 9FFC? What if I look at, like, 9F00 and look at, like, 20 of these? It's just all zeros. Like, oh, I'm so mad. I'm so mad. Why not? I guess there's a chance that our GDT is not allowing all memory access. That seems possible. So here in boot.s, what the fuck are we doing? Like, I haven't actually, like, looked at these values at all. But these could be, like, just bullshit wrong. That seems really likely, actually. Okay, so here we're in 16-bit mode. We clear intros. We jump to our LGGT adder, which is here. We set AX to 0. We move AX into this DS variable. We set the global descriptor table. We do some, like, we say, please be in 16-bit mode, and then we jump to our projected code adder at offset 8. So that's this entry in the GDT is what we say we're allowed to use. I think. Maybe it's this entry. I'll have to look that up. Probably this entry, actually. Then we do this stuff. We try to push the stack, and then just nothing happens. And that's where I get really confused. It's like push L, EBX is just not doing anything. I wonder if there's like a way to find out. So push x86 push value to stack not set. I don't know how to like. What if I like just execute a pop here? Can I do that? GDB execute assembly pop. Shell, no, you can't, like, doesn't include an assembler. Yeah, okay, that's pretty reasonable. So the other thing that's confusing me is why is this broken? But it wasn't broken before. What am I trying to say? This push is not observed, but I could call functions from within Rust. Maybe that's because in Rust they were doing they're not using the standard C calling mechanism that uses stack parameters. And so that could explain why some functions work, i.e. IOExit works, and that could be because it's like passing in the first argument as a register instead of on the stack. And maybe my stack is just fucking broken. That seems like possible. And so I wonder if there's like a way to validate this. Okay, let's just, can I just like do this and like see what happens? So here I GDB and disassemble here to 810. And I am here, so I can next instruction what? 1, 2, 3, 4, 5, 6, 7, 8, 9 times. And 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So now if I disassemble, we'll see I'm at this jump. And now I want to fucking see if my stack says anything interesting. So let's look at my registers. My stack pointer is at this guy, so much farther down than he was before. And can I say print as what, a like car pointer? Is it car star? Fuck, I've been in Rustland too long. My C is like dying. We're gonna print this guy, and we're gonna print like whatever, like 100 of them. He repeats 99 times. So let's just double check that, like, what is this plus 100? That should go far enough. Print, sorry, as hex. Yeah, that goes like over. So it looks like no matter how many times I fucking push EBX to the stack, I'm incrementing my stack pointer. It's moving, but nothing's getting written. which really makes me think that there's some sort of memory protection happening somewhere, and I just don't understand it. Writes just are not getting committed. I think... Okay. I think that's a good place to take a break. I'm 2 hours into stream, and I think that I'm gonna have to do some reading and some like validating of some stuff off stream that's kind of like not very fun to watch. I suspect, my suspicion at this point is that we set up this like thing called like the global descriptor table, and this guy sets up our like memory permissions, and it's possible we're like violating those in some way, or I don't understand this push instruction, and I need to do some reading about that. So I think I'm gonna call it there, do some off-screen reading, and come back with fresh eyes tomorrow. But I'm pretty. We have made some like good progress today, right? We went from having the CPU boot but not run any code to the point where like we're in Rust and we're debugging problems. We can run like our exit codes. We can like poke memory from within our second CPU and like get somewhat expected results, right? In debug mode, we saw print, we saw exits, but there is still some like confusion going on, specifically around like the stack not being respected. So I think we'll come back tomorrow and take a look at that. Thanks for watching. If you enjoy what you saw, I stream most days at around like 1 or 2 Pacific time for a couple hours. If you're watching on YouTube, the Twitch description is linked, or sorry, the Twitch link is in the YouTube description. And if you're watching on Twitch and you missed something, the YouTube channel is linked in the Twitch description. So I think if you go to like twitch.tv/Sparrowphoria. Oops. Let's maybe go here. How do I get to my channel? Click on this guy. Somewhere. How do I get to... Where's, like, my channel? Am I high? Yeah, down here. There's a YouTube link here. Yeah, down here. There's a YouTube... Oh, shit. Shut up, Nick. Yeah, so if you want to catch up, all VODs will go to YouTube. Yeah, thanks for watching. I'll catch you on the next one. Bye!